Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So this is the next video in our series about the analysis of variance, or ANOVA. To make the topic more manageable, I've divided this video into two parts. In part one, we will discuss the conceptual background using graphics and charts and an example problem, and then in part two, we will actually go into Microsoft Excel to conduct a hand calculation of ANOVA, and also solve our example using Excel's built-in data analysis tools. If you're watching this video on YouTube, you can download the Excel file using the link in the description so you can follow along when we get to part two. Now, in our last video, we took an in-depth look at the conceptual foundations of ANOVA and what it offers us. Prior to ANOVA, we were limited to conducting hypothesis tests about a maximum of 2 populations. ANOVA frees us of that limitation, permitting comparisons of multiple populations and even subgroups, or what are called blocks of those populations. Now, there are several types of ANOVA. In this video, we will be focusing on what is called the One-way ANOVA, and in a later video, we will discuss the Two-way ANOVA. It is important to note that One-way ANOVAs go by other names, such as the Single Factor ANOVA, and in experimental contexts, the Completely Randomized Design. These are all basically the same thing. Now, this video is very comprehensive. In part one, I will use several illustrations to make concrete the abstract concepts underlying ANOVA. In part two, we will go into Microsoft Excel to hand calculate the ANOVA, which, admittedly, you may never actually have to do. So this video offers a solid, comprehensive, conceptual foundation of One-way ANOVA, using an example problem with illustrations and graphics. So, if you are new to ANOVA or are still trying to figure out exactly what it is, this video is for you. So, sit back, relax, and let's go ahead and get to work. So the most obvious question is, why do we have ANOVA in the first place? So like I said before, to this point, we have been comparing 2 populations only. So we use the independent samples t-test or the matched sample or the paired t-test. Of course, limiting ourselves to the comparison of 2 populations as well, limiting. What if we wish to compare the means of more than 2 populations? What if we wish to compare populations each containing several levels or subgroups? Well, that's why we have ANOVA. It allows us to do those things. And remember, ANOVA is an acronym that comes from the phrase analysis of variance. So suppose we want to compare three population means, like we will in this example problem, to see if a difference exists somewhere among them. So we have population 1 here in the blue, population 2 here in the pink, and population 3 here in the green. And each population has its own population mean. So mu1, mu2, and mu3. So what we're asking is, do all three of these means come from a larger common population sort of in the background? Or is one of the means so far away from the other two that it is likely not from the same population? Or are all three so far apart that they all likely come from unique populations? So really it's about distinction. Are all three of these populations common to a larger population, or is one or all three of them different from one another? Now, I mentioned before there are several types of ANOVAs. So if you go into the data analysis section in Excel, you will see all those. So you will see ANOVA single factor, ANOVA two-factor with replication, and ANOVA two-factor without replication. Now, we will get to all those eventually, but for now we're going to be dealing with the first type. So in this video, we will be learning about single factor or one-way ANOVAs. They are the same thing. So if you go into Excel and see this menu in the data analysis tool, I want you to know exactly which one we're doing. We are doing the ANOVA single factor, or the one-way ANOVA. So here is our fictitious problem. So 21 students at the Autonomous University of Madrid, the AUM, in Spain, were selected for an informal study about student study skills. So 7 first-year, 7 second-year, and 7 third-year undergraduate students were randomly selected. The students were given a study skills assessment having a maximum score of 100. Now, as researchers, we are interested in whether or not a difference exists somewhere between the three different year levels. So we will conduct this analysis using a one-way ANOVA technique. So here is our basic chart. So you can see that we have a column for each year of students. So these are our columns, or sometimes they're called groups. And I mentioned in the previous video, one of the challenges of teaching and learning ANOVAs is that different professors and different textbooks will call the same thing different things. So sometimes these are called columns, sometimes these are called groups. Now, why is this called a single factor ANOVA? Well, if you look at this chart, this year of student is a single factor with sort of several levels to it. So that's why it's called a single factor. Now, within each year of student, we're going to select a random sample. In this case, 7 students. So, if you get the geometry of the chart, you can kind of understand how it's all put together. So we have 3 columns or groups. The single factor we're looking at is the year of the student, and within each group, we're going to be taking a random sample. So here is our actual data. So remember, these scores are out of 100, so you can see the 7 year 1 student scores on the left, the 7 year 2 student scores in the middle, and the year 3 student scores over here on the right. Now remember that these are random samples within each year, or each column, each group. That's why in an experimental context, this is called the Completely Randomized Design. So you may see that in your class or in your textbook, or of course both. So I went ahead and color-coded each year so we can keep them distinct. Now, if you notice at the bottom here, I have X bar sub 1, X bar sub 2, and X bar sub 3. Well, of course, that's going to be the mean for each column or each group. So each year will have its own characteristics. It will have its own mean and its own distribution or its own variance. So I went ahead and color-coded those to match. Now there will also be an overall mean, which is the mean of all 21 scores taken together. Sometimes this is called the grand mean. I call it the overall mean. Same thing. So there are several means under consideration here. We have the mean for each column or each factor level. It's the same thing because our single factor is the year of the student. So we have x bar sub 1, x bar sub 2, and x bar sub 3. Then of course we have the overall mean, or sometimes it's called the grand mean, which is the mean of all 21 scores taken together. So the first thing we want to do is find the mean for each column and the overall mean over here on the right. So the mean of the year 1 scores was 71.71. That's x bar sub 1. The mean of the year 2 scores was 75.29. That's x bar sub 2. Then x bar sub 3, which is the mean of the year 3 scores, was 76.57. Now the overall mean, or the grand mean, of all 21 of those scores taken together is 74.52. So that's the first thing we want to do when doing our hand calculation for the one-way ANOVA. So you can see our column means here on the bottom and our overall mean here on the right. Now if we take a quick look at the column means, what do we see? Well, we can see that the 71.71 over here for the year 1 students seems a bit odd. It seems a bit different than the other two. Now we don't know if that's going to be just due to natural variation or there's actually something there. That's why we're doing the actual ANOVA. So let's briefly go back and visit the idea of variance and its related concept, the sum of squares. So since ANOVA is by definition the analysis of variance, we should briefly review this as a concept. Remember that variance is the average squared deviation, or the average squared difference, same thing, of a data point from the distribution mean. So we take the distance of each data point from the mean, square that distance, add those together, and then find the average. That is variance. But if we take out that last step, if we take out the find the averages part, we are left with just the sum of the squares. So we would take the distance of each data point from the mean, square each distance, and then add them together. If we stop there, that is the sum of squares. So the sum of squares is variance without finding the average of the sum of the squared deviations. So it's the variance without that last step. And that's because sum of squares is a foundational component of ANOVA. So remember the formula for the sample variance. That's what we just talked about. It is the sum of the squared deviations divided by the sample size minus 1 in the sample case. So on the top we have the squared differences. So remember, x is a data point, minus mu, which is the mean. We take that difference and we square it. We sum all those up, and then in this case we divide by n minus 1. So on the bottom we're doing the averaging of the squared differences. Well, what if we take away the n minus 1 part? Well, we're just left with the sum of the squares. So each data point minus the mean, square it, do that for all the data points, add them up, and that is the sum of squares. So with the sum of squares of the difference between the dependent variable and its mean. That's all the sum of squares is. Now when we talk about sum of squares in the ANOVA context, what we do is we say this overall sum of squares is partitioned or split into two parts. So we call the total sum of squares SST. That's sum of squares total. Now that's made up of two components. The first component is the SSC. That is the sum of squares of the columns. So the columns, the between variance, the treatment sum of squares, that's what we're talking about. And again, this will make sense more in a minute when we look at the actual problem. Now the other component is the SSE, which is the sum of squares error. So this is the within or the error sum of squares. So the overall or total sum of squares in the one-way ANOVA is actually a combination of two things. The sum of squares of the columns, sort of between the columns, and the sum of squares of the error, which is actually the sum of squares within each column. So let's look at each one of these types of sum of squares using our actual data. So we'll start with SST, or the sum of squares total. So what we do is we find the difference between each data point, so all 21 data points, and the overall mean over here on the right-hand side of 74.52. We would then square that difference and then add all of those up. So we would have 21 squared differences. So here I only circled 5, but we would do this with all 21. So it's the difference between each data point and the overall mean, square it, and then add them all up. That is the sum of squares total. So if we look at this in the actual distribution, we have all 21 of our data points put together. And then we have the overall mean of 74.52 in the distribution there. So what we're doing is we are finding the distance of each data point to the overall mean. And then of course we square it. So we would have 21 squared deviations. Now here's the thing. When we take a distance and we square it, guess what we get? We literally get a square. So when we say sum of squares, we actually mean that literally. So we take every distance from the point to the mean, we square it. So we would have 21 individual squared distances on this graph if we actually did it. And then we sum up the area of all those squares. Now, I only mention that because it's going to become an important part later on when we talk about regression, because sum of squares is a very important part of regression as well. So sum of squares is literally squared distances when added together are the bunch of squares added up. Now let's look at SSC, which is the sum of squares of the columns. So this is the column or the between sum of squares. So in this case, we find the difference between each group mean and the overall mean, square those deviations, and add them up. So the SSC is the difference between the individual column means and the overall mean. So in this case, we'll have 3. So each individual column mean and the overall mean. So remember, the SST, or the sum of squares total, was the relationship between each individual data point and the overall mean. Well, the SSC, or the sum of squared columns, is the relationship between each column mean and the overall mean. So that would look like this. So the SSC is the distance from each mean to the overall mean. So you can see that there in the red. And again, in this case, we would literally have squares. So the squared distance, or the squared deviation, add them all up. Now the third type is the SSE. That is a sum of squared error, or the within sum of squares. So this is actually about the individual distribution around each column mean. We're not dealing with the overall mean in this case. So we would find the difference between each data point and its own column mean. Square each deviation and then add them up. So for example, we would have 21 square deviations in this case, because we would take each column score and then find the relationship between the overall column mean. So the difference between each data point and its corresponding column mean. Find the difference, square it, add them up. And then we would do the same thing for each column. That is SSE, or the sum of squares within. So what we're looking at here is the distribution within each column. So where each data point falls within each column. So this is what these three types of sum of squares look like when we put them all together. So in the first case, we have SST. Remember, that is each individual score, so all 21 scores, as they relate to the overall mean. So we find the difference between each score, the overall mean, square it, add them up. The SSC is a relationship between each column mean, there at the bottom, and the overall mean. So we find the differences, square them, add them up. And then the SSE is the relationship between each individual score and its own column mean at the bottom. So we find the difference between those two, square it, add them all up. So you can see the three different ways we're looking at the sum of squares. And the cool thing is that the SSC, the sum of squares columns, plus the SSE, sum of square error, adds up to the SST, or the total sum of squares. So you can see all the ways the data is sort of parsed when we do the one-way ANOVA. So this is an exaggerated view of the relationship between our three column means. So you can see that group 1, or the first year students, had a mean of 71.71. The year 2 students had a mean of 75.29, they're in the pink, and the year 3 students had a mean of 76.57, they're in the green. And I've kind of exaggerated the distance of group 1. So you can see that each distribution, or each column, has its own distance to the overall mean. So what we're trying to figure out here is the first year student distribution, those scores, kind of an outlier or sort of an oddball distribution? That's what we're checking for when we're doing the one-way ANOVA. Now remember, in the previous video I talked about why we cannot do 3 pairwise t-tests. So we could compare group year 1 to year 2, year 1 to year 3, and year 3 to year 2. That would be 3 individual t-tests. We cannot do it that way because the error, the type 1 error, compounds each time we do that. And we end up with a type 1 error rate of over 14%. So we have to do the ANOVA method when looking at this type of problem. Okay, so that ends part 1 of our video on the one-way ANOVA. So again, I wanted you to show how the data is actually arranged when we actually do the calculations. So we're looking at many comparisons within our chart. So we're comparing the column mean to the overall mean, we're comparing each data point to the overall mean, and we're comparing each data point in a column with that column's overall mean. And again, it's all about variance. So the squared deviation is a measure of variance. So the sum of squares is a way of quantifying that variance. So now that we have a comprehensive understanding of what the one-way ANOVA is and how the data points relate to each other, let's go ahead, go into Excel, and do this calculation by hand. Now I have some pre-made formulas that we can actually just sort of paste into Excel, but I will walk you through the actual computation of all those arrows and diagrams we had in the previous slides. So let's go ahead and look at part 2.